Hello guys, to represent this tutorial, my name is Big Jack, the physics tutor. So the question is saying alpha particles, beta particles and gamma rays are three types of radioactive emission. We have question A. State which type is Roman numeral number 1, the most penetrating, Roman numeral number 2, the most ionizing, Roman numeral number 3, part of the electromagnetic spectrum. So let's start with the most penetrating. So what you need to know here is that we have the alpha, right? We have the alpha. So as for the alpha, it can be stopped by a sheet of paper or a sheet of a plastic. So suppose this one here is the alpha and this one here is the paper. So which means when you talk of the penetration, this one here can't penetrate the skin, okay? The alpha particle can't penetrate the skin and it can't penetrate the sheet of paper and also a plastic. We also have the next one here, which is the beta particle. So as for the beta particle, it can be stopped by through the what? The sheet of paper, or it can penetrate through the skin. It can also penetrate through a plastic, but it can be stopped by a sheet of aluminium. Then we have the last one, which is the Y-ray, or Y-rays, which is also known as the gamma ray. So this one here can be stopped by a sheet of lead, the same metal lead. So PB, which is lead, which means as for gamma rays or Y-ray, it can penetrate through the sheet of paper and also the sheet of what? Aluminium, but it can be stopped by a sheet of what? Lead. Okay. Now, as you can see here, we can just conclude that gamma rays or Y-rays, this one here, it has the most penetrating. Okay, it is most penetrating because it can penetrate through the a sheet of paper or a skin or a plastic and also a sheet of aluminium, but it can be stopped by a sheet of what? Lead. Which means lead can be a good material to make a box where you can store these three types of radioactive. So the answer is just going to be gamma rays. Or if you don't want to say gamma rays, you can say or Y rays. Then the most ionizing. So what you need to know is that alpha, it has a nature to that of what? Helium. So helium has the mass number of 4 and the proton number of 2. Right? Then apart from that one, beta particle, it has a nature to that of an electron. So an electron is negatively charged. So an electron is negatively charged, right? So an electron is negatively charged. So even beta particles, they have a negative charge. But as for the alpha, it has a positive charge. Then a beta particle, it has a negative what? Charge. Alpha, positive. Then beta, negative. Then the last one, we have the Y-rays. So as for the Y-rays, it has a nature to that of a neutron. So a neutron, it has a zero charge. So we can just say zero charge. So we have zero charge, which means gamma rays or Y-rays, they have no charge, in short. Now, when you talk of ionization, ionization is just the ability of an element to form a cation or an ion. So when I say cation, it is a positive charge. Then an ion, it is a negative charge. Suppose we have sodium. We have sodium, it has a mass number of 23 and the proton number of 11. So sodium is going to lose 1 electron. So you are familiar with these things, okay? So sodium is going to lose 1 electron. So once it loses 1 electron, you are going to find that it is going to become an ion. Now specifically the cation. So you can say it is going to become a sodium ion with a plus on top here. So suppose we have magnesium. Magnesium, it has a mass number of 24 and the proton number of 12. So what is going to happen here? Magnesium is going to lose 2 electrons, okay? So once it loses 2 electrons, you are going to find that it is going to become magnesium ion with a plus 2 here on top, right? So now I want you to understand one thing here. Which one here is most ionizing between sodium ion or magnesium ion? So it is magnesium ion, okay? Why are we saying magnesium ion? This is because this one here is losing what? More electrons than sodium, right? So let's try to see what usually happens to the alpha, to the beta, and also to the gamma radiation. So for the alpha radiation, or alpha particles, I was saying it has a nature to that of helium. So what usually happens when an element or an isotope undergo alpha decay, what is going to happen is that the mass number will be reduced by what? By 4. And the proton number will be reduced by what? By 4. Case here, suppose element Y is undergoing alpha radiation or decay. So you are going to find that what is going to be produced here is a daughter cell. So for example, a daughter cell here, it is X. Now on top here we have the mass number being denoted by A. Then down here we have the proton number being denoted by Z. So what is going to happen here, for example, if the mass number of element Y here, it is 23. So if the mass number of element Y, it is 23, and the proton number of element Y, it is 11. So what is going to be formed here is that they are going to find that the mass number here will be reduced by what? By 4. Where are we getting 4 from the helium here? So it's more like the mass number of helium, then you say the mass number of Y minus the mass number of what? Helium. Since alpha particles, they have the same nature to that of helium. Even on part of the proton here, we are going to find that these 2 here for the helium or for the alpha particle is going to be subtracted from 11 here. As the result, what we are going to have here is just going to be 19 as the mass number, right? And then the proton number that we are going to remain with here is just going to be 9. Then at the end, you say plus C, the nature of helium, like this one here, at the end here. Okay, so now, we can just say, this one here, it is going to form a positive, it is going to form a charge of element Y is going to form Y plus C2, okay, Y plus 2. Where is this 2 coming from? From this one here, since the proton number is equal to the electron number. Okay, so what is going to happen? What is happening here? Element Y is losing how many electrons? It is losing 2 electrons. Okay, then let's come to, so this one is forming a cation now plus 2. Okay, now let's come to the beta particle. So as for the beta particle, since it has a nature to that of an electron, what usually happens here is that the mass number remains the same. For example, if element Y undergo beta decay, you are going to find that it is going to form an element X. So what is going to happen here, if the mass number here it is 20, or let me just say 23, then the proton number here it is 11. So what is going to happen here is that the mass number of an element is just going to remain the same. So in this case here we are just going to have 23. But the proton number will be added by 1. So in this case here we are going to have 12, and then plus the nature of an electron, which is this one here. Right, so as you can see here, this one here, element Y, is gaining what? An electron, and non-metals, they gain what? Electrons. So what is going to happen here is that element Y is going to form an ion, specifically a negatively charged, because it is gaining 1 electron here, the addition of 1 electron. Then let's come to the Y rays or gamma rays. So as for gamma rays, suppose we have element Y and it is having the mass number of 23. Then the proton number here, of course, we are just going to take 11. So what is going to be formed here is element X. Now what usually happens to an element when it is undergoing gamma ray decay or gamma particle decay, you are going to find that the mass number is just going to remain the same. Even the proton number is just going to remain the same, plus the nature of the neutron. Right? So that is what usually happens here. So now as you can see, this one here is just forming a zero. That's like neutron. Okay? So this one is a neutral atom. It is not having a positive charge or a negative charge on this part here. That's neutral. So the first one we had the alpha particle, which was having +2. And then the next one was the beta radiation or beta particle, which was having -1. And then the last one, it is just the Y ray, which is a neutral one. Now they are saying the most ionizing here. So the most ionizing here, it is just going to be this one here, which is Y to the power +2, which is the alpha particle. So the answer here is just going to be the alpha particle. Alpha particles or alpha particle. Then part of the electromagnetic spectrum. So the part of electromagnetic spectrum here is just going to be the gamma rays, right? So gamma rays or Y rays is part of the electromagnetic spectrum. And then let's come to B. Is saying, state what is meant by the half-life of electroactive material. So the half-life of electroactive material. Suppose you have been given 60 grams of the original mass of electroactive element. And then you have been told to find the half of this one here, which means you're just going to say half multiplied by 60 what? Grams. Then the answer is just going to be what? 30 grams. Now in talk of half-life, it is just the time taken for the original mass to be halved, right? I'm saying the time taken for the original mass to be halved. So we have the original mass here, which is 60 grams. Now the time that is going to take these 60 grams to be halved to 30 grams, that is what we are going to call as the half-life. So we are saying answer. So we are saying time taken for the original mass of a radioactive element to be halved. That is what half-life is. Question 2. Question 2 is saying, state the difference between magnetic and non-magnetic materials. So magnetic materials, they attract, or they are attracted to a magnet, and non-magnetic materials, they don't attract to a magnet. So an example, when you consider the magnetic materials, an example you can take as steel. So steel is an example of a magnetic material. Apart from steel, we can also say cobalt. So cobalt is an example of a magnetic material. And then when it comes to non-magnetic materials, an example, the first one is just going to be wood. Then the last one is just going to be plastic. Or in addition, you can also say copper. Copper is a non-magnetic material. Copper can't be attracted to a magnet. Insulated wire is wrapped round a core, as shown in figure 13.1. A current is passed through the wire to form an electromagnet. So we have the core and the coil. So there is a difference between a core and a coil, right? Yes. So the first question is saying, Roman numeral number 1, suggest a suitable material for the core. So the suitable material for the core, it is just iron. Okay? Why are we selecting iron? Iron don't form a permanent magnet. So iron does not form a permanent magnet. But if you choose steel, steel is going to form a permanent what? Magnet. So steel forms a permanent magnet, while iron don't form a permanent magnet. Roman numeral number 2, state 2 ways by which the strength of electromagnet may be increased. So the first one, it is by increasing the current. By increasing the current. Then, number 2, by increasing the number of turns. So when you talk of turns, we just mean the number of what? Coils. The number of coils, these wires that they have wrapped. Yes. So by increasing the number of turns. By increasing the number of turns. So that is our final answer. Let's come to question 3. So question 3 is saying, figure 2.1 shows the decay curve for a radioactive substance. So we have the original mass, in this case, the original mass, it is 120. Okay, 120. Then, at the end here, it's just ending at 7.5, somewhere there. The first question, question A, determine the half-life of the radioactive substance. So if you can remember very well, when you talk of half-life, the time taken for the original mass to be halved. So if the original mass here, it is 120. So you can just say half multiplied by 120. Then the answer is just going to be 60. Now this 60 is somewhere here. So let me just draw a line. So this is our line. Now the time taken for this 120 to reach 60 grams or 60 activity per count per minute. So we can just say, let's also, since time is in the x-axis, so again we are going to draw a line from this point here up to this point here. So let me just draw that. So now at what time is this one here? What time is this one here? So if you can see very well here, for in a 2 centimeter box, there are 5 small boxes. There are 5 small boxes, which means every box, a tiny box is representing 0.2, right? Now this one is at 4. This one is at what? 4, which means this one can be something like 1.6 minutes. Okay, so the final answer is just going to be 1.6 minutes. Where are we getting 1.6 minutes? Like a 2 centimeter box is just something, this one here. Yeah, now if you see properly here, you're going to find that in a 2 centimeter box, we are having small boxes which are 5, right? They are 5. So now a tiny one, a tiny box is going to represent 0.2. For us to have one here, which means each box, each tiny box is representing 0.2 for us to reach at what? 1. So now we are here, and this one is 1, okay? Which means we can just say, if this one is 1, the next the next line, which is this one here, it is going to be 1.2, right? Then the next one is going to be 1.4. Now this one here is just going to be what? 1.6. That is where we are getting 1.6 from. So we can just conclude that the time here, it is just 1.6 minutes. So they have included the minutes here. Let's come to B. B is saying Roman numeral number 1, the radioactive substance can be described using nuclide notation. So we have A. This A is representing the mass number or the nucleon number. Then Z is representing the proton number or the electron number or the atomic number. When a beta particle is emitted, a beta particle is emitted. So when they say when a beta particle is emitted, you need to think about the equation, the general equation for the beta emission. So what usually happens to the beta emission? The proton number will be added by 1. Let me just say yes, the atomic number or the proton number will be added by 1. And the mass number is just going to remain what? The same. So we have, when a beta particle is emitted, the number Z increases by 1. They have even indicated here. So state and explain what happens to A. So what usually happens to A, like the way I was saying A remains the same. A remains the same. So state. So remains constant. Remains. Then why is it going to remain the same? Because it is going to be added by what? By 0. Right? It is going to be added by 0. Then let's come to Roman numeral number 2. The radioactive substance also emit alpha particles. So alpha particle is positively charged in nature. Beta particle is negatively charged in nature because it has a nature of an electron. Then they are saying describe the nature of an alpha particle. 2 marks. So I'm just going to put 2 answers here. The first one, alpha particle is positively charged in nature. It is positively charged in nature. Apart from that one, alpha particle, it has strong ionization. Alpha particle has strong ionization. Likewise, let's come to the last question. The last question is saying, figure 15.1 shows a simple circuit. The lamp is light and there is a reading of 0.2 amps on the ammeter. So you have this lamp here, and this lamp here leads 0.2 amps on the ammeter. A variable resistor is now placed in parallel with the lamp. So suppose we have a variable resistor here. Since they have said it is placed in parallel, so that is how you place a resistor in a parallel way. The resistance of the variable resistor is adjusted until the reading on the ammeter is 0.4 amps. So this 0.4 amps, it is more like a total of the resistor and also the lamp. Determine the current in the variable resistor. So they are asking us to calculate the current here in the variable resistor. Now, since we have 0.4 amps, which is the total current of all these 2 appliances, and then we also have 0.2 amps of just the lamp. So you can just say, when we add 0.2 amps for the lamp plus the current, so let me just use any letter like R for the current in the resistor, we are going to get which one? We are going to get 0.4 amps. So in short, just say 0.4 amps minus 0.2 amps for the lamp then the answer that we are going to get here is just going to be 0.2 amps for the resistor or variable resistor. So that is how we answer. Then as for B, the resistor of the lamp is 3.0 ohms. Calculate the EMF of the cell. So EMF, electromotive force, is same as the voltage. Now since we know that current is equal to voltage divided by the resistor, so you can make V the subject of the formula. So when we make V the subject of the formula, it is just going to look like this. V is equal to current multiplied by resistance. So we are getting the voltage here. What is our current? The current for the lamp. The current for the lamp here, it is 0.2. So we are going to put 0.2 amps multiplied by the resistance that we have here. It is 3 ohms. So we have 3 ohms. So when I multiply here, I'm just going to get 0.6 volts. So here they have included the units like that. So it is 0.6 volts. Then the last one, the potential difference across the variable resistor is parallel with the lamp. With the lamp is the same as the potential difference across the lamp. Determine the resistance of the variable resistor. So we need to determine the resistance of the variable resistor. Now what you need to know is that when the components are in the parallel or are in parallel under circuit diagram, they have the same potential difference or the voltage, which means the lamp and also the variable resistance, they are having the same voltage, which is this one here, 0.6 volts. Current is equal to voltage divided by resistor. So when we make this HARA the subject of the formula, the equation is going to be resistance is equal to voltage divided by current. So we have the voltage here, which is 0.6, and the current of the variable resistance. Let me say the variable resistor, it is also 0.2 amps. So let's do that. Where we are having V, we are going to place 0.6 volts. So we have 0.6 volts. Then where we are having E, which is the current, we are going to put 0.2 amps. Then when we divide, we are going to find that the answer is just going to be 3 ohms. So it is 3 ohms. Here they have included the units. So that is our final answer. So if you see this video to be useful, kindly subscribe for more videos like this. Peace.